Alright, so this is attempt number 2 at movement science. So a lot of people have asked me a lot of questions with the free body diagrams, and I've been helping a lot of people, and more people asked to be helped, so I figured I'd just post a video and that should help everyone. So if you use the textbook, that one, I'm also recording on my phone just in case, so now I have the iPad and the phone because there's no chance I'm recording this a third time. So basically if you want to look on, I'm using the problem on page 102. I'd say I'd wait for you to find the page, but you can just pause the video. Just kidding, I wasn't paused. Yeah, so you can go to page 102 and I'm going to use the question with the lady pulling down on, what is it? The cable. Alright, so I think the ones that we did in class that with like the straight arm with the forces just going up and down were probably a little easier, so I'm going to do the ones with the angles. The same thing applies, except you don't have to break it up into between like an x and like a s of x and s of y or whatever to get the x and y axis portions. So those would be a little easier. These are a little more challenging, but ideally the same things apply. So I don't know if I should talk that in there. Also, if you're watching this because you think I was going to record a funny video, I'm not, so don't waste your time. This is literally just to help people who have problems with the free body diagrams. Alright, so should I go over basics or just get into it? I'll just get into it. So if you look at problem, whatever the problem is, the one on page 102, this is basically what they give you. So you have your forearm coming down, the hands holding the cable, the weight of the cable, the joint force, and then the muscle force. And then what you need to do is you need to find the joint force, the muscle force, and then find the angles of the joint force. So they give you a couple things in the information. They give you a couple things of information in the book, but this is the basic way of, this is what they give you with minus the x coordinate and the y coordinates. But don't worry about that for now, because what I found for most of you guys is you had trouble finding where the actual right triangles are. So this is what I would do, and I'm going to do it on the board like this. It makes it easier, but if you want to just keep the diagram like this the whole entire time, do that. So on a piece of paper, I drew what they gave me. You got all your forces coming out, where they're coming out, the angles that they gave you, blah, 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 blah. Now, we need to determine, it's in my pocket, the x and y axis. Alright, so we need to determine the x and y axis. So this is our forearm, it's going down, once again, it's pulling from the cable, these are basically all the forces. The first step is to determine where your x and y axis is going to be. You might be wondering why I have a giant whiteboard in the back, but I'm using the separate one. You'll see in just a couple seconds. So on my piece of paper, I would draw this out, and then I would make this my x-axis and my y-axis and just kind of go off of that. So we'll do that, and we'll label that. So this is going to be our y-axis, and that's going to be our x-axis. Now, so now that we determined that basically all of our forces are going to be going perpendicular too. So if you're good at conceptualizing, basically your y forces are going to come perpendicular, which means like a 90-degree angle into what you just determine your x-axis to be. But I find it easier that if you did this on a piece of paper, let's just make it visually appealing. So let's rotate the piece of paper and draw it like that. Well, now it's a lot easier to draw all the angles because you can make them, you know what I mean, go right into each other. So this would go like this. And I'll do this bigger on the board. Well, this is just a really quick one. But now it's a lot easier to see where all your right angles are that you're drawing. So that's one way I would like to do it. I'm going to do it like this in large on the board just so everyone can see. This is going to be the worst video ever, but whatever. Hopefully it helps. So yeah, so you have your diagram that you draw on your piece of paper, and then just rotate it and make it easier, because this is now, hey, this is your x-axis. That's going to be your y-axis. So it's going to be easier to conceptualize and basically find your all your angles. And draw all your triangles. So, let's do that. Alright, so, now if you were to rotate your paper, this is what it should look like. So now here's your forearm. Here's your elbow joint. You're going to have your J coming in this way. Actually, I'll make this even easier for you. I'm going to use the same colors that they used. Alright, so your J is going to be the blue one. That's going to be coming in at an angle. Once again, I'm not doing anything, I'm just redrawing whatever the picture is that they gave you. So that's your J, and obviously this will also not be to scale. M is your muscle. That's going to be coming in this way. That's your M. And what was cable's green? Yeah. You got your cable coming in this way. That's your C. And then in black, you have your weight of the forearm. It's going to come down like that. And that's your S. Alright, so basically what we did is we took the picture they gave us, we set our X and Y coordinates, and we just rotated it. So now it's easier to make all of our angles and find your right triangles. So, remember, to make our right triangles, everything's going to be going this way. So now, this hasn't changed, just your view has changed. Remember, this is our x-axis, and anything going up is our y-axis. Now, a little help with the angles. Basically, let's say that this is our axis. Remember, ignore this for now. But you have your x-axis here, your y-axis here. Don't quote me on the terms, but I'm pretty sure this is right. I took physics a very, very long time ago. But this is your resultant. Basically, that's your final direction and force. So let's say I had a pin right here. I put a pin over here. Now, we can even go north, south, east, and west, if this helps you. But basically, I have a pin, and I'm pulling it right now in the northeast direction. Well, there's two components of that. There's the east portion, which is this direction, and then there's my north portion. So this, if I wanted to make my resultant, I'd have to walk this many units to the right and this many units up, and that would give me my final resultant. But in science or physics or math, whatever you want to study, this is your resultant going that way. That's your hypotenuse. Over here is going to be the x portion of it, so we're going to call it your f of x. And then over here going up, that's going to be your f of y. So essentially, if I pulled a certain force that way and a certain force going up, that would be my end resultant. I don't know if that's how they called it, but that's why I would have named it that. So what we want to do for these, because they're all at angles. If this was like that first problem yesterday, it's like, oh, like, well, there's this force going down and there's no x or y direction, we wouldn't have to find any of our s of y or our c of y or any of that stuff. But I'll explain that. I just want to make sure that you guys understand this part first, that every single angle that we're going to have over here is going to have a y portion and an x portion. I'll leave that for there. But, okay, so let's start with our s. Now, our s is going down and to the right. So, we would have to go, remember, this is our y-axis, we would have to travel down, I don't know if that's enough or thick enough to see, but we'd have to travel down that distance, and we'd have to travel over that distance. Now this portion going down is going to be our s of y, our y portion of the s force, and then the portion going to the side is going to be our s of x, because it's going to the right. Let's do the c. I'm going to keep the black marker. So now the c is going up and to the left, so we have to go up in the y direction, so that will be our c of y, and then we're going to have a portion going over to the left in the x direction, so that's going to be our c of x. Same thing here, so let's do our muscle. Now there's two ways to do it. I'll do it this way. I'll just continue as if it was going on. So we're going to continue our muscle going this way in the x direction because it's going up and to the left. So that's going to be our m of x, and then traveling up in a y direction, our m of y. Now the j one's a little different because it's not being pulled from here, it's being, it's going in the direction of the joint. So it's traveling down and to the right. So we're going to go over to the right in the x direction, so that's going to be our j of x, and then we're going to go down in the y direction, and that's going to be our j of y. So basically these, we're going to break everything down eventually into all of our x forces and all of our y forces, and then we'll be able to figure out the resultant forces, well, the force of everything, all of our angles, and all that other jazz they're going to ask us. Okay, so now let's get some angles in. So what did they give us? I'll write everything they give us over here. So it is known, so we know that our S is going to be 17 newtons, our C is going to be 66.75 newtons, and I believe they gave that to us in pounds, and then we just converted from pounds to newtons, but they did that in the textbook. Our M is, well, we don't know, we're going to find that eventually, and then also our J, we also don't know, our joint force. Alright, so then the angles that they gave us are theta is 25, so right over here, theta is equal to 25 degrees, beta, my fancy B, is 70 degrees, alpha is 20, and mu is unknown. Alpha, not as fancy, and mu, we don't know, so we'll put a question mark. Alright, so this is our beta. Our beta we found out is 70 degrees. We have our theta, which is this angle. This is 25 degrees. This angle is 20 degrees. And that's all we know. And this is eventually mu, but we don't know what this is yet. let's start with S. Now the way we find S is we're going to break down our S into the y component and the x component. So I'm going to do that probably right here just because it's close. Now something you should know is you didn't have to draw your right triangle like this. You could have drawn it also if your x went that way and then your y went down. You're going to find the same answer. But the only thing is, so here's our triangle. Here's our right angle. Now, in order to calculate and find these sides, we have to work with the angle inside the triangle that we made. Now we know that if this whole thing obviously is a 90-degree angle, so if this is 25 degrees, what's our other angle? 90 minus 25, so that's going to be this angle right here, and that's going to be 65 degrees. We know S is 17 newtons, and I'll do this once, but I always know that it's going to come out that it's the hypotenuse times sine or cosine, whatever you're doing, of the angle. But just to show you why that is, so you know I'll just do it once over here. So we know that when we do our trigonometry, we have so, ka, tawa. So let's use our sign. So we have, let's make our triangle again. That is not a triangle. That's a quadrangle. I'm not funny. Alright, so there's our right triangle, there's our angle. So here's our triangle. Across from the 90-degree angle, that's our hypotenuse. Across from the regular angle, that's our opposite side, and then going with it, adjacent with it, is our adjacent angle. So whenever you're finding your angles and sides and all that stuff, you set up your proportions. So the sine of whatever your angle is, so in our case it's going to be sine of 65, is going to equal your opposite, your O, which in this case is S of x, divided by your hypotenuse, which is your h. We know that's 17 newtons, because we're going to find that. Now when you're going to find this, you go multiply by 17 on this side, that's going to cancel out, and you're going to get your S of x is equal to sine of 65. Your S of x is equal to sine of 65 times 17. So I'm going to do it always really fast. It's always going to be your hypotenuse times your angle to get whatever side you're looking for. But that's math-wise why I'm writing that. I'm just going to skip a step, just to go a little faster. Not like I'm going fast at all, but just showing you now. All right. Now the other confusing thing that I know people have problems with is people always think, oh, well, the one going in the x-axis is going to be cosine, and the one going in the y-axis is going to be sine. So they get things confused, like, okay, well, S of x, that's going to be cosine of 65. But you have to remember, our triangle is really like that. So the sine is your opposite, which in this case is your S of x over your hypotenuse, which is 17. So although it's labeled S of x, it's always going to be the sine. When you're finding it, is always going to be whatever is opposite of your angle. So just remember that. Who cares that it's labeled S of x? I can call this S of e, and it'll just be, S of e is going to be my sine of 65. So, finding this one. We have your S of, so we're finding S of x first. So we have S of x is equal to, and it's going to be our hypotenuse, which is 17 newtons, times the sine of 65 degrees And when you put that in on your calculator, you get 15.407. Remember, we're newtons, and then I rounded to 15.41. So 15.41 newtons, and I will square that for our S of x. S of y. So now we have the y component. So same thing, we're going to do the hypotenuse, which is 17. So 17 newtons times, now we're doing the adjacent, because remember, here's our angle that we have. We're doing the adjacent to 65, so that's going to be our cosine, because I erased it, but cosine is adjacent over hypotenuse. So cosine of 65, and then you multiply that out on your calculator, and you get 7.184 newtons, which I will round to 7.18 newtons. Now, sines. We went down right here to get to our resultant. So our y portion is going to be negative. So, because we're below the y-axis, that's why our y is negative. So we're going to box that off over here. The x is still traveling in the positive direction. It's going to the right. So anything to the right or up is positive. Anything down or to the left is going to be negative. So we're going to make that a negative 7.18 newtons. Once again, I just do it this way because I memorized it like that. They use hypotenuse times the sine or cosine of your angle is going to find both those sides. What I just did over there was just to show you how we got to the hypotenuse times it. It was just when you set up your proportion and you go to solve for the side, that's what it says. So I just saved you a step. Alright, so that's our S of x, that's our S of y. We're done with that. Let's do our C. And I will do it, I don't know where I'll do, but also with the S of y and the S of x, if you want to do S of x going this way and S of y going down this way, you're going to get the same answers. The only thing is, instead of using sine of 65 and the cosine of 65, you're going to use that angle because that would be the triangle that you made, not ours. But the answer should be the same. If not, I don't know, some ancient philosopher messed up. But I'm pretty sure that's going to be the same exact answer. So that's your S component. So let's do your C component. I'm going to do it right here just to make it a little easier. Or just so I have enough room to write over there later on in life. So your C of y. So this is where we made our right triangle, and same thing, you can do the whole entire thing going this way and up. If you want to use 70 degrees, perfectly fine. It's however you choose to draw your triangle. This is how I drew mine, so we're going to do it this way. So if this is 70 degrees, remember this whole thing over here is 90 because I drew it perpendicular to the y-axis. So if that's 70, this is 20. Good work. So that's going to be 20 degrees. So basically all of our calculations are going to be using sine or cosine of 20 degrees. C, we know what C is. It's given. It's 66 point, can't read my handwriting, 66.75. So this is going to be 66.75 newtons. So let's find our C of y first. So our C of y is going this way. Here's our angle. Is it opposite or adjacent? Or is it the hypotenuse? It's not the hypotenuse. So we want to find, we're going to find our y first, because that's what I wrote over here. You can find your x first if you want, it's really up to you. But our C of y is going to be our adjacent angle, or our adjacent side to our angle. So our adjacent, so ka, adjacent over hypotenuse, we're going to use cosine. Anytime you use your adjacent side, you're using cosine of the angle. Anytime you do the opposite side, you're using sine of the angle. So C of y is going to be our hypotenuse, which is now 66.75 newtons times we're going to do that one first, the C of y, which is going to be our cosine of 20 degrees. And that becomes 62.724. Oh, happy birthday, Elon. This is my birthday, July 24th. And we're going to round that to 62.72 newtons. And that's why it's going in the positive direction, so it's going to be a positive number because it's going up above our mini fake plane that we made. All right, C of x. Well, C of x, now we're finding that direction, and that is our opposite because it's opposite to our angle. So once again, we're going to write the hypotenuse, which is 66.75 newtons times the sine now of 20 degrees. And that gives you, survey says, 22.829 newtons, which we will round to 22.83 newtons. And it is going to the left, so it is in the negative direction. So that will be a negative 22.83 newtons. All right, so we have all of our S components. We have all of our C components. Now we got to find our J and M. Now, we don't know what the J force or the M force is. So what we're going to do is we're going to find the torque, and we're going to be able to cancel one of them out. Now the reason we do that is torque is basically your force times your moment arm. So we can pick any place on this whole entire, or our forearm, but what our free body diagram, whatever you want to call it. So I'm going to pick this place right here. Now, any place you choose is going to cancel out that force going into that location. And the reason is because if I use every single force from this direction, this is going to be times something, so force times something. This, well, the distance from this point to this point, there is no difference, so it's going to be 0. So that's why when we multiply by 0, this actually cancels out. So we're not going to find a J force when we find the torques. But there's a distance to S, and then there's a distance to C. So whenever you have two variables that you need to find, which is basically going to be our J and M, pick one of the places to find your torques at that location, and that's going to cancel that out. And then using algebra, we can find between our C and S, we can find our M. But if you wanted to, you can find the torques right from this angle, and then your M would cancel out, and you can find your J, S, and C. But we're going to follow the book. All right, so now we're going to find the torques. So the way we do that is we know that the sum of all torques is 0. So we write our equation, sum of all torques is equal to 0, and then basically everything that comes off of our line, or our x-axis, or our whatever we're using, so in our forearm in our case, is going to be there. So the torque of S is going to be your S force times the distance away from our point, which we use as our joint over here, so times that distance. The C is going to be the C force times that distance. The muscle force is going to be the muscle force times that distance, and then the force of the joint, which is that force times no distance, that's going to be 0. So, when we do this, we're only concerned with the y coordinate right now. All the S of y, the C of y, the J of y, and the M of y. And I'll tell you why. I know, so corny. Alright, so let's say that this is our forearm right here. Your joint's right there. Now, torque basically is going to be what affects this will move our arm. So if I have a force going down this way, so I'm going to push down, it rotates. I'm putting torque onto my line, okay? If I have a force going up and I can make it even further this way, it rotates what I'm doing. The force is being applied to this. Now, I'm going to switch this way. So that's why we do the Y direction. Why don't we do the X direction? Well, same thing. Let's say this is my arm, here's my thing. If I pull to the left, or to the right, ideally if this was stationary, like if I put a pin through this, we're not moving anything. See, I'm pushing really hard. But I can apply up and down all the time, and then that will move it. So that's why you use your Y coordinates. So, some forces. Remember, we're using all of our C of Y, S of Y, J of Y, and M of Y. Just to save steps, just remember that torque is equal to your force times moment arm. And your moment arm is really just your distance. So a force is measured in newtons, and the moment arms are measured in distance away, which is in meters. So basically all of our torques are going to be Newton meters. So my piece of paper is right here. So let's go once again. 0 is equal to our torque of S. So our torque of S is going to be, remember we're using S of Y. So our S of Y is, we found, negative 7.18. So we're going to write negative 7.18 newtons, and that's going to be times your external moment arm at S of Y, and that's given to be 0.18 meters. So I'll write 0.18 meters. So this whole thing right here is our torque of S. Okay? Then you're going to add that to, now the book says external moment arms and internal moment arms. It seems that basically your internal moment arms are just like your muscle is an internal force, as opposed to the cable, which is being applied externally, and the weight, which is being applied externally. But it's really just your distance. It really doesn't matter what you call it, unless Dr. Ford cares, in which case put where it should be coming from, but you'll get the same answers. Okay, so that's our T of S. Then we have our torque at C, and that is going to be, so we have our force, remember, because our torque is our force is C of Y going up. So C of Y is 62.72 newtons. Right. 62.72 newtons. 72. Wow, that's much. 72 newtons times our distance, and our distance from our joint that we established to C is 0.33 meters. And that's our torque at C. Then we have our torque at M, and that's going to be, so our M force in the Y direction, we don't know what it is, but we're going to solve for it. So we'll write our M of Y, which is unknown for now, so we're going to just leave it as M of Y, and that's going to be times your distance. Now the distance for this one is, because it's to the left of our joint, it's going to be a negative number. And that distance is negative 0.02. So negative 0.02, and our unit is meters. plus our last one, which is our torque of J, and that's going to be our J in the Y direction. Well, J in the Y direction, we also don't know, so we'll want to leave it as J of Y, but it's not going to matter in 2 seconds because of this, times, and a dot is multiplication in case anyone was wondering. I tried to make it very distinctive what the decimal point is. So our J of Y in the direction, well, how many, if we're in the same spot, there's no difference. So basically our distance from here to here is 0 meters. Remember, this is our torque of M, and this is our sub M. I'll leave it like that. And this is our torque of J. Okay? So these are basically all of our terms. Now because that's a 0, that's why that cancels out. Because this could be any number in the world, based on math, anything you multiply by 0 is always 0. Even if it's 100 billion, quadrillion, million, whatever, times 0 is still 0. So, we're just going to put an X on that. So now we don't care. So, then we're going to basically multiply all these out and add them up. So when you do that and you combine like terms and all of that jazz, you're going to get 0 is equal to 19.4052 minus 0.02x. Or I changed my x, but really I guess it's your m of y. I'll erase that just so nobody gets confused. X is just a variable, that's what I just wanted to call it, but m of y. Okay, so that's when we combine like terms. So basically, negative 7.18 times 0.18, do that because you do what's in parentheses first, then you add that to 62.72 times 0.33, that's going to be this term over here, so that should come to 19.4052, and then negative 0.02 times m of y, like I said, just x, is just negative 0.02 y times m of y, because we don't know what it is. Then, so this is just, once again, just general math. I'm going to multiply 19, or I'm not going to multiply, I'm going to subtract that negative 19 from this side. That's going to cancel out. And what you do to one side, you got to do to the other, so you get negative 19.4052 is now equal to, bring this down, negative 0.02 m of y. So now what we got to do is we have to get the m of y by itself, so we divide this by negative 0.02. That's going to cancel out, and you're going to get m of y is equal to, that is a y, divide this by negative 0.02, and you get 970.5 newtons. Because remember, we only found the force. The torque is a newton meter, but we just found the force of m and y because here's your distance over there. So that's your meter, that's your newton. We only have our newtons. Alright, so m of y we just found is 970.5, and remember, it's going in the positive direction, so it's going to be a positive number. Now I believe in the book, when I find it, the book rounds to 970.5. I don't remember exactly what I got, but rounding wise, that's what they're rounding to. And then the next two things we're going to do are also the way the book rounds, which is really dumb, but we're going to just stick to the book so you can follow better. Alright, so we just found our M of y, which is our y portion of our muscle force. And remember, that's going up, and so that's in the positive direction. That's why it's positive here. And remember, it's just the force. That's the force in the y direction. That's 970.5 newtons. So now what we're going to do is we're going to find m. So we're going to bring this over here. I'll probably just erase stuff as I find more room. So over here, our m, that's what we're going to find right now, is, let's see. So let's look at this over here. We have our m of y, and they gave us the angle at 20 degrees. Now they said that 20, if you continue that line, that's what 20 degrees is. That's just in the book. So you have your angle, and you have your opposite, and we're going to find our hypotenuse. So, opposite, hypotenuse. Opposite, hypotenuse. So, sine. Sine is equal to opposite over hypotenuse. So let's do that. So over here you have your m. So your opposite, which is going to be your m of y, is equal to your m times your sine of 20 degrees. Now, this is exactly what we just did over here. So we had our opposite side. So remember, using when we did our s, we had our opposite side, m of y, our opposite side, opposite to the angle, was equal to the hypotenuse, which we're going to find is going to be m, this one right here, times your, right? Then we did cosine on that one, but same thing. We're going to do our sine at the of the angle. And ideally, I guess I should be doing that one because in this one, the s of x in this one was the opposite side. So, remember, opposite side, we're doing sine because it's opposite hypotenuse. So we have our m of y is equal to our m times the sine of 20. So we just found our m of y to be 970.5. So 970.5 is equal to our m, which we don't know, times the sine of 20 degrees. Basic math, divide by sine of 20 on this side, that will cancel out. You have your m is equal to, and then over here you divide by sine of 20 degrees, and you get, this is the problem. Ideally, in a real world, you should keep whatever your calculator says. So when I did this, I found it to be, I'm saying, is this what I found it to be, or is this what they found it to be? So the book says 2,854.41 newtons. The reason it says that is because if you take your calculator, which is right here, if you just do sine of 20 degrees, and remember, make sure you're in degrees, not radians, sine of 20 is equal to 0.342020143, or there's a lot more numbers, but that's what your calculator says. If you leave that in your calculator, that's going to be your most accurate answer. What the textbook did is they rounded sine of 20 degrees to just 0.34. On a test, I'm not going to do that. That's ridiculous because you wouldn't want to round that. So if you did it correctly, if you did 970.5 divided by sine of 20, 970.5 divided by the sine of 20 degrees, you should get 2,837.55217. The book, though, however, says 2,854.41. 54.41. I'm just going to go with the book, but that's why. It's because the book rounded to sine of 20 just to be 0.34, which is really dumb. I didn't write the textbook though. Whatever. Don't ask me. So just know that's how you solve it, but I'm going to keep with the book's answer just so you can once again follow everything along. So the book says that it is 2,854.41, and remember that is going to be a force, so that's in newtons. So that's our M. Next, we're going to find our M of x, which is the other side. So we're going to go this way. M of x is equal to, you have your, so now we're going to do the cosine, because we're looking for our adjacent side, and we know our hypotenuse, now we know our hypotenuse. So you have your hypotenuse adjacent, cosine adjacent over hypotenuse, and obviously we have our angle. So we're going to do a similar thing. So M of x, our cosine portion is going to be our hypotenuse, which is M, times the cosine now of 20 degrees. Okay? And now we can sub it again. M of x is, well, we don't know, so we're going to leave this as M of x. And that's going to be equal to M, which we just found is 2,854.41 newtons times your cosine of 20 degrees. And similar to before, the book rounds, I got 2,854.41 times the cosine of 20. I got 2682.268014, but the book rounds because they're dumb and whatever, but we'll keep with their answer because they rounded whatever the cosine was to only 2 digits. So when you do that their way, you're going to get M of x is equal to 2683, so 2,683.15 newtons. And let's see, x is going to the left, so it's going to be negative. We'll box that as our answer for that one. So now we found all of our m's. We found our m resultant, we found the y portion, we found the x portion. We know the s, we know the y portion of the s, the x portion of the s. We know our c, we know the y portion of our c, and we know the x portion of our c. Now we just have to find the j. So the cool thing we can do now is we can break everything up into all of our x's and all of our y's, because we know that all of them are going to equal 0. Because remember, we're in equilibrium right here with the cable. So what I'm going to do next is I'm going to erase all of this. So pause it if you need to make sure that you got it all, because I'm going to erase it and then I'll just rewrite all the terms that we have right here on the left just so it's easier to see. With some TV magic, basically I just rewrote everything that we solved just so I can make room for the next step. Now, what we're going to do next, you want to make sure that all your signs are correct. So I want to go through just one more time just to make sure that everything was good. So our S we had is 17 newtons. That was the S force, but when you break it down to the Y is negative. That's going down, so that's correct. X is going to the right, so X should be positive. That's good. C, You have your C of 66.75 newtons. Your Y is going up, so that should be positive. Y is positive. And your X is going to the left, so that should be negative. C of X is negative. That's good. Muscle. Muscle force we found was 2,854.41 newtons. The Y is going up, so that should be positive, but the X is going to the left, so that should be negative, and it is. So we're good there. Reason you want to make sure your signs are good is because now we're going to change everything, and we're not going to change anything, but we're going to solve only using our X forces and our Y forces, because in our system over here, anything to the left, or pulling from the left and pulling from the right, should equal 0, and anything pulling up and pulling down should equal 0, because sum of all of our forces at equilibrium should equal 0. There's no movement. Alright, so let's find the sum of forces on the whole system. So, we're going to find our Y direction first. So all the forces, the sum of all of our forces in the Y direction should equal 0. Now, right now we have to take everything that is in our system. So we have our muscle, we have our joint, we have the S, which is our weight of the forearm, and then we have the C, which is the cable force. So remember, we only care about the Y's right now, so our muscle, our joint, our, what else do we have? Our weight of the arm, and and then we have our cable in the Y. So now we just plug it in. So we have 0 is equal to, so our M of Y is going over here, M of Y, 970 newtons. So 970.5 newtons plus our J of Y, well, that's the only thing we haven't found out yet, so plus J of Y, or X if you want to change it to a variable, and plus your S of Y. S of Y is right here, and we found that to be negative 7.18. So negative 7.18 newtons. And then our C of Y, which is this one right here, and C of Y we found to be 62.72 newtons. 62.72 newtons. So now what do? We combine like terms. So if you add all those terms except for obviously the J of Y because we don't know what it is, so negative 7.18 plus 970.5 plus 62.72, and you should get 1026.04, and then also plus our J of Y, and that is going to be equal to 0. That's an equal sign, not a negative. So then what do we do from here? We have to get JY by itself, so we subtract from this side. 26.04. That cancels out. What you do to one side, you're going to do the other, so you get negative 1026.04 is equal to JY. So JY is equal to negative 1026.04 newtons. And we box that. And let's make sure that makes sense. So we have a negative in the Y direction. Now you might think, hey, that means that our force should be over here, but it just means that it's traveling in the negative direction. It's really going this way. So it is negative, it's going down because we're starting here. So it's like almost as if we made our coordinate system over here for this one. It's going negative and then it's going to go positive x, but we didn't find x yet. But we know when we do, it should be positive. So our j of y we just found to be that negative number. So now we're going to do it again, and we're going to find our sum of forces in the x direction to find our j of x. So similar idea. Sum of all of our forces in the x direction are going to be equal to 0 because everything's in equilibrium, so everything should cancel out. And that is going to be equal to our m of x plus j of x plus x of x plus c of x. We're going to have 0 is equal to m of x is this way. It's our negative big number, negative 2,683.15 newtons, plus our j of x. We don't know, so we will leave it as j of x, or x variable, whatever you want to call it. You can call it first letter of your first name, any variable you'd like. S of x is, so plus S of x is 15.41 newtons, 15.41 newtons, and C of x is negative 22.83. Negative 22.83 newtons. So you add all these up, and remember you're adding a negative plus a positive plus a negative, just to make sure we're all clear. And when you do that, you should get 0 is equal to negative 2,690.57 plus, and then our j of x, and then we bring this over to this side, so we're gonna can't get this to 0, so plus 2,690.57. That cancels out, and you have over here j of x is equal to, and then the positive that we just added over here. So it's going to be 2,690.57. That is going to be in newtons. And that is our j of x. And just like we said before, it should be a positive number because it's going down and to the right, because it's starting essentially over here. So it's to the right, positive. So that makes sense. Alright, once again I'm going to erase this, and I'm just going to add it up to our list over here. So pause it, take a picture, whatever you want to do, just so we can do the next step. Alright, so we just found the j of x portion, we found the j of y portion, so now we're going to find our actual j force. So we found, once again, the j of y, the j of x, and we need to find our joint force. So if we know two sides of a right triangle, what can we do? We can do Pythagorean theorem to find out our hypotenuse, which is our resultant force. So we know the x, we know the y, we're going to put that into a squared plus b squared is equal to c squared, and that's going to give us our j. So we're going to do that right up here. So we have, to find j, a squared plus b squared is equal to c squared. So we have a, doesn't really matter, so let's just do, let's go in the same order. So j of x squared plus j of y squared is going to equal j squared. I'm just substituting a, b, and c into our actual sides. So j of x, we have 2,690.57 newtons squared. Don't even worry about the newtons for now. We're okay. We'll add it in at the end. So that's squared plus j of y, which is negative 1026.04 squared is going to equal j squared. Remember, when you square a negative number, negative times negative is a positive. I quote a movie, but I don't want to seem old if you don't know the reference. Basically, you do all of that. And I have some numbers down here. Some very large numbers. But I think the first one you get like 105277 or 758.082. Then you get blah 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 7239166.925. But basically you add all that up, so let's just assume that is the number. Could be wrong. 7239166.925 is equal to j squared. We want to get j by itself, so we'll take the square root of the squared. That will cancel out. You'll have j is equal to, take the square root of that whole thing, and that should be, survey says, j is equal to 2879.57 newtons. And that is now our j force. That is the force of j going in that direction. Alright, so last step, all we have to do is find that last joint angle. So what I'm going to do is I'm just going to redraw this. Now remember, your j of y is really, it's the same thing coming down this way, it's just crumbled up, and your j of x is going this way. So I'm going to redraw the whole joint angle and force on that. I'm just going to redraw that right here. So you have your joint force coming in, so that's your j. You have your y portion coming down, that's your j of y. And then going this way, you have your j of x. We know that is a 90-degree angle. And this is our mu, which is what we're going to find. So what I figure would be fun is your book uses cosine to find this, but I'm going to use sine just so you get the same answer. So, no matter what you do, you can do it either way. So you can go, remember you got so, ka, toa. You can use any one of these ratios to find your angle. So, if you wanted to do the sine, remember your sine is your opposite over hypotenuse. So, the sine of mu is equal to your proportion of your opposite. So your opposite is going to be your j of y divided by your hypotenuse, which is j. You'd find that proportion and you do the inverse of sine to find that answer. If you wanted to use cosine, you can do the cosine of mu is equal to the adjacent angle, which is your j of x, divided by your hypotenuse, which is j. And if you want to use the tangent formula, you do the tangent of mu is equal to your opposite, your j of y, over your adjacent, which is your j of x. I'm going to solve it using the sine, but they should all come out to be the same exact thing. So your sine of mu is equal to the proportion of your j of y, which we found to be negative 1026.04. Sine's not really going to matter, so it's not a big difference. So that number divided by, and especially because you're dividing, so it's just really not going to matter much. Your j, which is that number, 2879.57 newtons. And we do that, and you get, I go 1, 0, 26.04 divided by 2879.57. I got my proportion, which is negative 0.356317, whatever. I'm going to do second, sine, which is going to give my inverse function. So that's going to give me u, or mu, is equal to, of second answer, that what we just did. And I get 20.871, blah, 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 blah. So I would just round that to 20.87 degrees. You tell me, I guess comment, or however I post this, I don't know yet. Do the other ones. Ideally, you should get a same answer, or a similar answer, maybe just rounding wise. So they got 21.57. Like I said, maybe it's just rounding again. I don't know, but it's close enough. So that's how you get the angle. So that's your last angle. And that was everything you had to find to review everything. Basically, we had some problem. Somebody was going to lift something from a cable. They're holding it like this. So you had the cable force, the weight of the arm force, the muscle force, and the joint force. We drew a nice free body diagram, which looked like, when it's nice and pretty, this. First thing we did is we decided to make the forearm our x-axis, and obviously perpendicular to that to be with the y-axis. If you have trouble drawing triangles, I say, hey, take your piece of paper and make it horizontal. And just go off this to try and remember, all your y's are going to be perpendicular to your x-axis. Make all your right triangles, label them all s of x, s of y, and all, same with c, j, and m. Do that, and eventually you'll get this. Start with what you know. Fill everything out. Start with, so far every single time we've done it, we've been looking for M and J. They can give you one of these and maybe make you find for S or C or whatever the scenario is, the weight that's in the palm of the hand or the weight of the forearm. Anything like that, you can figure it out. It's just doing similar things to what we just did. So, we started with S. They gave us the hypotenuse and the angle, so we were able to find our x and y components of that. Similarly, we did the same thing with C. We found the x and y components of that. Once we had those two, we used torque to find our M. The way we did that is we took the torque and we made this our joint over here. So we took the force of everything times the moment arm, which is really just the distance away from the point you chose. Because this is the point we chose, this point was 0, we didn't have a J term. We were able to add up the y component of S, the y component of C, and then solve for the y component of M. The reason we did that is because if we made this our joint, if we pulled this up or down, that would actually move our arm. But if you go X and Y, it's not going to change anything because this is our pivot point right here. That's not going to have any effect on the system. So we found that. That gave us our y force because we know the angle. We took the angle and the y component to find the actual m. And then we just did that again to find the m of x. So we had all of our m filled out now. We figured that out. We figured our s. We figured our c. Last we had to do is find out our j stuff. We did the sum of all the forces in the x direction and the y direction, because all of those have to equal 0. So that gave us our j of y and our j of x. We did the Pythagorean theorem to find out what the j resultant was. And then once we had all of our j lines, we were able to set up a proportion, do the inverse function of sine, cosine, or tangent, however you chose to do it, to get the last remaining angle. Now, seriously though, if anyone has any questions, I don't know how I'm posting this yet, but comment below, call me, beat me if you want to reach me, whatever you need to do. No one has beepers anymore, that was from Kim Possible, but you get the idea. Thank you very much.